All right, today we are going to be starting a new chapter, and this chapter is going to be about surface area and volumes. Okay, so our ultimate goal by the end of this chapter is going to be able to calculate the surface area and the volume of three-dimensional figures. Okay? Before we can actually get into calculating the surface area and the volume, though, we need to make sure that we all have some common vocabulary when it comes to three-dimensional figures. So for today, that's what we're going to focus on, three-dimensional figures. You should all have a note sheet in front of you that would have the outline of this as well to help you take some notes on this. So first off, a polyhedron. A polyhedron is a solid with all flat surfaces that enclose a single region of space. So a solid with all flat surfaces that encloses a single region of space. For example, the classroom that you are currently sitting in is a polyhedron. It is a solid, it has all flat surfaces, and we just enclose one area of space. Here would be a diagram of our classroom. Okay, so this would be a polyhedron. Now, all polyhedrons are going to have faces, edges, and vertices. The face is the flat surface. Each flat surface should be a type of polygon. So, for this diagram of the classroom, each flat surface is a rectangle. So the face of this polyhedron that was drawn would be a rectangle. Edges. Edges are the line segments where the faces intersect. So the edge is the line segments where the faces intersect. So over here, every time you see two faces intersect, that would be called an edge. So there is an edge. This would be an edge, an edge, an edge, and so on, all the way around that entire diagram. In the classroom, the edge would be where the floor and the front wall meet. That would be an edge. Where the floor and the side walls meet. Where the ceiling and all the walls meet. Those are edges. Vertices. Vertices are the points where the edges intersect. The point where the edges intersect. These are also known as the corners. So here, all of these points would all be vertices of this polyhedron, otherwise known as the corners. Okay? Polyhedron is a very general name for what we are going to be dealing with. We're going to be dealing more specifically with things like prisms and pyramids. So we need to get a more specific definition of what a prism is. A prism is a special type of polyhedron so it's a polyhedron with two parallel, congruent bases, which are each a face, and then all other faces are parallelograms. So for example, the diagram that we drew could be a prism. We could have two. So there would be our bottom base and our top base. Those are parallel to one another. They are congruent to one another. And then all the other sides here, those are all parallelograms. A regular prism is just a prism whose bases are regular polygons. And regular, recall, regular means congruent sides and congruent angles. Okay, so we are going to start naming some prisms and getting the idea of how we name prisms. Prisms are going to be named by the type of base it is. So we want to look at the type of base we have, and then we name it that way. So in this chart, these are all prisms. So this first one is an example of a triangular prism. This is a triangular prism because if you notice, our two parallel sides there are both triangles. So those are our two bases. So the shape of our base is a triangle. Rectangular prism is the next one. Rectangular prism, you could really look at any of these sides to be bases. So this could be a base, and that could be a base up there. Those are parallel to each other. The shape of the base is a rectangle, so we call it a rectangular prism. If you look at our next shape, the pentagonal prism, the two sides that are parallel, you see are both pentagons. So those are the shape of your bases, so it's a pentagonal prism. And that's really the way how we name all of these. So if we have an octagon for our bases, we would have an octagonal prism. If we have a hexagon for our bases, we would have a hexagonal prism. If we have a dodecagon as our base, we'd have a dodecagonal prism. So we always name the base, add a AL at the end, and then prism. Okay? A pyramid. A pyramid is where it's another special type of polyhedron. So it's a polyhedron where all the faces, except for one, which is the base, intersect at one vertex. So it's a polyhedron where all the faces except one intersect at one vertex. And the pyramids are also named by the base, the same way how we named our prisms. So for example, here I can draw us a pyramid. So there's my base. I'll put a point up here saying that that's where all of my faces are going to intersect. I can draw lines down to each of the corners. And so this would be a rectangular pyramid. We say rectangular because the shape of the base is a rectangle, and it's a pyramid because all the faces intersect at that one point. That's the key to making a pyramid. And then there are some other solids that are kind of special solids. We have our Platonic solids. Platonic solids are where all the faces are congruent to one another. So these, there's a finite number of these. So we can have a tetrahedron. Tetra, that prefix means 4. So there are 4 faces here, and each face is a triangle. And that's what our tetrahedron looks like. A hexahedron, otherwise more commonly called a cube. Ooh, that marker clicked. Let's see. So a hexahedron, also known as a cube, has 6 faces, and each face is a square. Octahedron. Think about our the prefix octa. That usually is 8. So there are 8 faces here, and each is a triangle. And specifically because all the faces have to be congruent, this has to be an equilateral triangle. Same with the tetrahedron. These should also be equilateral triangles. A dodecahedron. Dodeca, that's our prefix for 12. And those are all regular pentagons. There are some dice that are set up like dodecahedron that have 12 different numbers on. Some of you might have played with those before. They're in some games. And then the icosahedron, this has 20 faces to it, and each face is an equilateral triangle. And wow, I spelled the icosahedron incorrectly on here. It should really be spelled I-C-O-S-A and then hedron. So icosahedron. I was just missing that A in there, I think. All right, so those are our Platonic solids. All right, and then we also have a few other just special types of shapes which are based off of our circles. So based off of our circles, we can have a cylinder. A cylinder, if you notice, we have 2 parallel bases. And they are circles. A cone just has one base. It's one circular base. And then we have one vertex. They all meet. It also all meets up at that top point. And then our sphere is like your typical basketball, baseball. The technical definition for a sphere is a set of all points equidistant from the center. The set of all points equidistant from the center. And this would be the set of all points in a plane. Or not in a plane, in space. So it's 3-dimensional. Now what we're going to do next is we're going to identify the solid. We're going to name the base. We're going to name the faces, the edges, and the vertices. So what we first have to do is we have to decide what it's called. So here we see that we are meeting up at one vertex point. So that means that this right here tells us that we have a pyramid. So we have to look at the type of base we have. We see 4 right angles. We do not see anything that indicates it is a square, though. So we are going to call this a rectangular pyramid. Okay, so we're going to start with the base. The base is going to be the shape of a rectangular. So the base here would be A, B, C, D. So our base is rectangle A, B, C, D. Faces are all of our other sides. So our faces here, if you take a look, they're all triangles. And we have 4 of them, so we want to name all 4 of them. So starting off with this front one, we have EAB, so triangle EAB. If you think about kind of moving to the right, we then would have triangle EBC. The one sort of in the back would be ECD. And then the one off to the left would be EDA. Triangle EDA. So those would be our 4 faces. Our edges, you want to do this sort of in a systematic way. So I'll first name the 4 edges along the base. So the 4 edges along the base would be AB, BC, CD, and DA. I just went right around AB, BC, CD, DA. And then we would name the edges going up to the vertex. So we would have AE, BE, CE, and DE. And then we want to name all the vertices. The vertices are just all the corners or all the points. So this would be A, B, C, D, and E. All right, so that's how we identify the solid. We name the bases, faces, edges, and vertices. Now your information does not have to be in the exact order as this information up here. Your information also, for example, when you're naming the triangles, the order in which you write the points does not matter. Next one. So here we see it's definitely not a pyramid because we're not meeting up at a point. So this is a prism. And you have to figure out what our shape of our bases are. So here I see these 2 sides are the parallel sides, so those are triangles. So we would call this a triangular prism. Okay, so for here we have 2 bases. The bases are your 2 triangles. So your front triangle is triangle ABC, and your back one is triangle DEF. So those would be our 2 bases. Our faces, so what's connecting the triangles? Well, if you look at it closely, each face has 4 sides, so it's a parallelogram. So one of the faces, if we look at that one that was just highlighted, would be BEFC. Make sure you go in order, BEFC. So we went order around. The one off to the left then, we could say CFDA. So CFDA. I don't care which letter you start at, you just have to make sure you go in order around your parallelogram. And the one on the bottom, we could call ABED. So those are your 3 faces. Edges, once again, you probably want to do this in sort of systematic way, so we'll start off by looking at the edges of the bases and naming those first. So I'll clear that off so it's a little easier to see. So the edges of our bases, so of our front triangle, they would be AC, CB, and BA. Our back triangle would be DF, FE, and ED. Now we have to do the connecting lines between our prism. So we would also have in here AD, CF, and BE. And last but not least, our vertices would be A, B, C, D, E, and F. So that's what we would do for our triangular prism. Last prism here, name it. Well, this is definitely a cone. Base, well, its base is that circle, so we would say it's circle S. Faces, there are no faces. so we wouldn't even have to list them. Edges, well, there aren't really any edges either, so we don't have to list those. So we just have a vertex. Vertex is point R. So for a cone, we only have our base and our vertex, which should make sense because that is all we listed down for the definition of a cone was a base and a vertex. It did not have any edges or any faces. All right, then last but not least, we are going to talk about something called the cross-section. The cross-section is the intersection of a plane and a solid. So a plane is just a flat line or a flat piece of paper. So here I've got a cylinder drawn out 3 times. For the cylinder, we want to try to get the following shape from the cross-section. So first I want to get a circle. So what you have to do is you have to picture where a circle is in a cylinder. And a circle is the shape of your 2 parallel bases. So for us to get a circle, we would have to put a plane through that would be parallel to both our bases. And then we would have a circle for our shape. An ellipse, which is an oval type shape. So we want a circle that's elongated. To get that, we would have to cut this down diagonally through, because then we would have a circle or an ellipse that would be elongated. A rectangle. Well, a rectangle, we could cut straight vertically with our plane. If we were to do that, we would have a rectangular shape being cut out of there. So this is all about being able to visualize it correctly for how we would find the correct cross sections. All right, so you will have an assignment which will be due tomorrow, and then tomorrow we will continue talking about some 3-dimensional shapes.